Okay, well, I think we'll get started. For the people who came late, are there any questions on the homework due on Thursday? Okay. So today we're going to be talking about files, file I/O, file formats, that sort of stuff. Just briefly, basically just some very basic, how to do some basic file input and output in Python. Talk a little bit about, the theory of file systems, how they're constructed, but just at a very basic level. And then talk about various file formats for saving your data. Okay, so you're probably all familiar with this. Files are organized in a file system, a hierarchical file system. The files themselves contain your data, and they're organized into a hierarchy of directories that help you find those files. Directories are can be thought of as files too. They're just special files that point to other files. And just terminology, a path is just the sequence of directories to locate a file in a file system. Okay. And Unix calls them directories, Windows and the Mac call them folders typically. So I have a little example here of just two folders. Folder 2 having one file called note.txt, folder 1 having a file called world.txt, and another directory called hello. It's a subdirectory with its own little files in it. Okay, so now how do we manipulate the files of file system in Python? So you want to use the OS module. And that's because the file system is provided as part of the OS kernel. So you can make a directory with makedir, same as the Unix command. And then instead of cd to change directory, you use chdir, so changedir. Change your current default directory. And this just sets, if you create a file that isn't an absolute path, just sets where that file defaults to being created, which directory it defaults to being created in. And there are certain special kinds of directories. So for instance, the double dot just means cd into the parent directory of my current directory. So basically go up one level. Okay, so I want to create a file. So you use the open command with the file name. Since this doesn't start with a slash, it's a relative path, and it's relative to your current directory. So basically, your current directory will be inserted in the front. And then we pass a section option, just the W string, just a string containing W, and that just means open the file for writing. If you don't pass the second argument, it'll open the file for reading. So you can read from the file, but you can't write to the file. So here we say we want to write a new file. Okay, and then it's just simply a matter of you call the write method on the file. So f.write to write a string to the file. And then when you're done, you close the file. If you don't close the file, you might not all of your stuff might end up in the file. And this just says you're done with it, write it to disk, save it. Okay, so this is writing a file. Now, sometimes you want to this overwrites the file, right? So if you do this a second time, you'll end up with the same, the original contents over it. So oftentimes you want to just append to a file, say, add something to the end of a file. And so then same thing, just change the mode to A. So open it in append mode, not in write mode. But otherwise, the API is the same. Okay, reading a file is similar, but instead you just change the mode to R instead of W, and you can admit this too. As I said, if you just admit the second argument, it defaults to R. But now, if you want to, typically when you read file, you'll want to read a line from a file. So there's the read line method. That'll get you the first line of the file. If you want the entire file, just use read instead of read line. Okay. Now, if you want to read and write to the file simultaneously, the mode is R+. And now this lets you do something. This is a little fancier. You probably, it's not used very often in practice. But now you can move both write to the file and move around the file with the seek command. So seek command basically means move your current, pointer in the file, around by this many bytes. So basically this says, okay, so I open the file. Now I'm going to go to the first byte, write something at that position, and then read a line starting from the next character. Oh, sorry, no. I guess there must be separate write pointers and read pointers, right? So here, by seeking, I've moved to the first character. So remember, the file contains hello. This moves to the first character. I write an A, so I basically overwritten the E with A, right? So that when I read it out, I'll get hello instead of hello.
And if you enter the seek again, would it move forward one more, or is it absolute to the beginning of the file?
Yeah, these positions are relative to the position of the file. I mean, sorry, they're absolute. Yeah.
Okay.
Yeah. Okay. Again, this is kind of obscure. I tend to avoid it, but we just include it for completeness. Yeah.
So F0 means H.
Sorry.
So if you go to F0,
that would go to the
means H. The first.
Yes. 0. Yeah. Seek 0 will take you to the beginning of the file.
Okay.
Okay, so just very basic overview, reading and writing in Python. So now we'll talk a little bit more just about file systems in general. So basically, a file system is an abstraction to a physical medium, typically non-volatile, but it doesn't have to be. So, it can be memory, it can be spinning disks, flash these days, a DVD, a tape. For long-term storage, etc. There's all sorts of various physical formats that you can expose through a file system. And basically, all they are is essentially just a huge number of bits. And a file system is just a way to organize the access to this storage, which in and of itself is basically just a huge array of bits. So basically, you have to write essentially information onto the disk to describe what the disk actually contains, and this is called metadata. Basically, you write special patterns to the media to describe how that media is organized and what's on it. Okay, so we've got this, we've got some media, and it's just basically a bunch of bits. So we could try to come up with our own simple file system. So what we're going to do is we're going to just have a very simple file system, which is just at the beginning of the disk, I'll write a series of records that describe the files on this disk. And so the record will just be the name of the file, and then a number saying where it starts, which number bit it starts at, and then the number of bits that file contains. And and then it'll just have another record for the next file, etc. So just a very simple file system. You know, you put the metadata at the front, and then the data, the file data at the end of it. Does that make sense? So file name, starting point, so this says I, so go to this bit number, and that's the start of the file, and then use this size n bits, and that's the size of the file. Okay, so a very simple file system. And again, that stuff, the records stored at the beginning are just what's called the metadata. File systems, you know, they'll have the name, the size, you know, where it is on the disk. Some file systems will store the type, although Unix tends not to. There may be dates associated with the file, say when it was created, when it was last accessed, etc. There may be permissions on the file. I mean, these are typically, you know, file systems are typically shared resources. So if you have lots of users using a system, you have to manage, you know, let people protect their data and not have other people accidentally overwrite it. So you'll typically have permissions associated with them as well. And there can be a bunch of other stuff, right? So if you go back to our little simple example, we've got just a linear list of metadata records, and that's our file system. But imagine now I've got the file system is, you know, a billion files. To find a file, I now have to go through each record, look at the name, and see if that's the one I'm looking for. So I just have to do a linear scan through all the records, which is extremely slow, right? And so this is where the directories come in. Now you basically say, okay, well, I'm going to now put in other special files called a directory that will then point to files or directories. So essentially now I can just put all my top level directories at the beginning and then jump. And then if I'm now in a subdirectory, I jump to its contents on disk. And then that's another list of files, and then I can jump again. So it's a way of basically speeding up the search by arranging it in this hierarchical structure. Instead of just doing a linear scan, now I can do a pretty fast search. Does that make sense? Okay, so that's the file system on disk, but what happens when we actually access a file? Typically, this is what's for, so basically, first we have to find the file in the directory. We have to check the permissions in the file. Can I access this file? Am I allowed to see this file? And then we have to find, then we just have to say, okay, I'm allowed, but now I have to find where is it actually living on disk? Where is it physically located? And once I've got that, then the kernel will create a handle and initialize a pointer, basically saying where I am in the file. And this handle is what open returns. Okay, if I'm writing a file, so I've got this handle, and I want to write to a file. That data I give it has to be converted to some sort of stream of bytes, because as far as the disk, the disk is concerned, the file system is concerned, it's just bytes. There's no structure to it. It's just a sequence of bytes. So those bytes are buffered. This is for what's called buffered access. You can have unbuffered access too, and skip this step. But when you call open in Python, that's typically buffered. So those bytes are then written into a buffer. The pointer is updated, saying, you know, how many bytes you've written in. And then if you reach the end of the buffer, you say, okay, I'm now going to flush this to disk and actually write everything in the buffer to disk, and then go back to the beginning of the buffer and start writing again. Okay, reading is similar, just in reverse. So again, it's buffered. So when I read a bunch. If there's nothing in the buffer, then I have to call out to the kernel and get basically a block of data, put it in the buffer. And then if I'm reading, since I grab data in blocks, I have to and I read, say subblocks of that data, then I have to have a pointer saying, well, I've only read, I've got this much data in the buffer, but I only read this many bytes. So I have to keep track of how many I've read versus how many I've actually read off disk. And that's where the file pointer comes in.
Why use a buffer at all? Why not just work directly from?
Because it's just faster to grab chunks. You can imagine. I was going to talk about this a little bit later, but you imagine a spinning disk, right? There's some latency, and I have to move these heads to the right position. And then once I'm there, then you can just stream a bunch of bytes off as it spins by. So it's just much more efficient to grab a whole chunk at once versus grabbing one byte here and one byte there. Right? So yeah, it's just sort of a caching layer for speed.
Is that true for flash memory also?
It's going to be less true for less of an issue for flash, but it will still do it in chunks, right?
Flushing a buffer could mean one of two things. It could mean user space flushing it, basically handing off to the kernel. Now the kernel gets to decide whether it gets written. Does it use fsync or something to force it to flush, or is it really in this context just meaning, okay, kernel, it's up to you now?
Yeah. This is not. Yeah, okay. I'm not talking about anything at the low. Yeah. So there's no fsync. Yeah, this is more just a high-level overview, just very sort of basic file system intuition. Okay. So so now if I'm closing the file, then I'm going to say to the kernel, okay, I'm done. Take the data, do whatever you want with it. Metadata gets updated, and then the buffers will get released when everything's done. Right? Basically, just cleaned up. Okay, now I started talking about a little bit about this. Disk I/O is basically is usually your slowest part of your code. Because you think the processor is going so fast these days, and disk I/O has not. Disk storage has been expanding incredibly, but disk speeds have not. They've essentially stagnated. So everything, you can think of it like mailing a letter. You basically every time you're asking, you're reading or writing data to disk. It's like you're writing a letter, mailing it off, and then waiting a few weeks for the response. So here's just a little example. I can write, writing a string to disk. I can either write each individual character, opening the file, writing the character, closing the file, or just write it all at once. And this is going to be much faster just because the kernel can batch it to disk. So the idea is to try to do everything in memory that you can, hit the disk as little as possible, and then when you do, hit it with as much as you can. Hit it with as much as you can. Okay, so that's the file system. Any questions? It's just, like I said, it's just trying to give you a little bit of sort of intuition about sort of more, sort of how file systems are structured, but at a very high level. Okay, so that's the file system. So now we're going to talk about files and encodings of files, right? Because as a file system, as far as the file system is concerned, it's just a bunch of bytes. It doesn't care what it is. To it, it's just bytes. But to us, we need to now put, like there's structure in the file system, there needs to be structure in files to organize data. So at the simplest level, you can just treat it as bytes. This is typically text files. But here again, we have to now assign, every byte to a character. So there has to be some encoding, even for a text file. Or we could just write it in raw binary, just dump whatever's in memory to disk. And then, so that's raw, raw binary, or we can have sort of structured binary, which includes some metadata about the binary. And we'll talk a little bit about this. Next slide. Okay, so for text, typically, you're starting out, it's going to be ASCII. And ASCII is a 7-bit encoding. So there are 128 possible characters, 7 bits. 95 of those are sort of screen printable. Others are sort of instructions for like moving around, like, or like, hit the bell. Sorry, make a beep, right? So it's 7 bits, but it's encoded in 8-bit bytes. So it's not 7 bits, 7 bits, 7 bits. It's 8 bits. So there's basically 1 bit wasted for each ASCII byte. So right off the bat, you're only 82% efficient because you've thrown that extra bit away. It's especially bad if you're using text representation of numbers or floating point, right? Because if you're writing basically in base 10, you typically have like 18 bytes to store a number versus 8 bytes if you just do it in raw binary. And Ramsey's talked about that in the second lecture, how floating point is encoded in memory. So not only is the storage inefficient, but now you have to convert back and forth between them, right? And that itself is also slow. And it can also be non-exact, right? Again, in the second lecture, I think we went over that, if you type in 0.1 in Python, that doesn't exactly equal 0.1, right? You'll get 0.1 and then a bunch of zeros and another extra 1 at the end. So you can even be possibly losing data with a text encoding. Okay, so that's ASCII, and ASCII was, invented. This is the I forget the acronym, but first letter is American. So it was invented a while ago for basically doing American English. So you can only do letters and numbers, no accents. You can't do New Yorker English. You want to get that joke? So no accents, just letters and numbers, no accents. So now there's another encoding called Latin 1, which now uses the entire 8 bits, adds another 128 characters, and can now basically do most of the Western European languages. So it can add all the like the vowels with accents, etc., things like that. But that's been superseded these days by what's called Unicode, in particular UTF-8, which is now so Unicode is basically trying to encode every language in the world, living and dead, into one character set. And UTF-8 is basically an 8-bit variable length encoding of this. So in ASCII and Latin 1, each character is the same number of bytes, just 1 byte. So if you move in bytes, that's another character. Each byte is a character. Unicode doesn't have the concept of characters in the same way that ASCII does. And its basic code point representation is 32 bits. But that's very inefficient. So basically you have other formats like UTF-8 and UTF-16, which are essentially compressions of this. And the way you do it is now it's a variable with encoding. So a code point could now be 1 byte, or it could be multiple bytes. And Python can deal with the various encodings. If you put in, you can write your source files in multiple encodings if you tell Python what the file encoding is. Otherwise, it'll assume ASCII. So you put in this special comment line and says, I wrote this file in Latin 1. or I wrote this file in UTF-8. Otherwise, it'll assume ASCII.
Only use UTF-8.
Yes. Yeah. These days, yeah, UTF-8 has basically supplanted everything. Right? Okay, so that's text encoding. So now, but most of the time we're going to be storing numbers, and for that, I try to dissuade you from storing them as text. So okay, so now we need to store them as binary, not as text. Okay, so I could just write them, and as I said, yeah. So yeah, if you encode them in if you write numbers in ASCII, it's very inefficient. So here's just an example. If I'm writing 128 million doubles to disk in ASCII, 173 seconds versus just binary 6 seconds. And for small files, this is fine. Or for small files, this may not be really an issue. You may actually want to see the numbers, the individual numbers. But for, if you're storing big things to disk, big arrays to disk, you're not actually going to be looking at the individual entries, right? You're going to be manipulating them as a whole. So the fact that the files aren't human readable isn't an issue anymore. Okay, so you could just dump the contents of memory to disk. I've got this array of numbers. I'm just going to just dump the raw bytes to disk, and that's my file. That's my file format. And you can do that. The problem is the file format is now just stored in your memory, your personal memory. And if you forget, you could potentially lose information. Or if you give it to someone else, they're not going to know necessarily how to read this file. So you come back a year later and you go, well, what is actually in this file, right? How did I structure it? So you'll need some sort of format of your binary data, some sort of you'll need to write some sort of metadata along with the data to tell you what the data is and how it's structured. So we'll talk about a few formats for the rest of the class. First one is something called Pickle, which is Python specific, and would be, this would be a nice thing to use if you're storing small amounts of Python specific data like dicts and lists, that sort of stuff. But it's not particularly efficient. It's backwards compatible, but if you write a file in Pickle in a recent version of Python, that's not guaranteed to be readable by old versions of Python. Numpy has its own binary format called NPy or NPZ. There are file formats that aren't Python specific, and we're going to talk about two: NetCDF and HDF5. NetCDF is typically used in the climate, or started off in the climate community, but there's nothing climate specific about it. And HDF5 is similar, but more sort of complex. And in fact, these days, NetCDF is actually built on top of HDF5. But the advantage is NetCDF is sort of a simpler API. HDF5 is quite complex, and if you have, very complicated structured data, it may be appropriate. But for I tend to prefer NetCDF because it's a little simpler. Okay, so we'll talk about these and how you use them. So first off, Pickle. It is basically a text format, but it tries to be, it tries to do base 64 encoding instead of just regular ASCII encoding, so a little bit more efficient. It's in the Pickle module, and again, it's good for if you want to serialize basically Python, structures like dicts and lists, and send those, and send that data to other people using Python. If you want to, it's not really good if you want to use it in a program that isn't Python. Okay, so here's an example. So I've got Pickle. I'm going to make a big array. So I start off by using the normal file API. I open a file handle, writable mode. And now I use this Pickle dump function. So I dump the object I want to dump into the file pointer that I open. Okay, and then just close the file. So pretty simple. So that's writing stuff in. Getting stuff out, again, I have to open a handle. And instead of dump, I used load. Okay, pretty simple. There's the NumPy routines. It's hard to see. It's hard to see here, but this is actually the size of the file is actually much bigger than the size of the array in memory, because Pickle is not a particularly efficient format. So if you write it out in NumPy's format, which you can get through this save command. I think we're missing the import. Yeah. So import numpy.save. So if you look at this, if you're basically saving the same array in this format, you'll see it's down by a factor of about 5 smaller. And that's because now it's storing it in just the raw binary format. Sorry, not a raw binary format, but in the minimum binary format, or the same binary format it's stored in memory instead of expanding it into a text format. Okay, so and the API is similar to Pickle. There's a save function and a load function to get it back out. So this can be handy, but again, this is Python specific. If you're sharing it with other programs or people, I would prefer not to use this. Right, so, but let's just go through the API. I showed you the save function. So save the file name and then the object you want to save. So that's for saving one object, one NumPy object. Now, if you want to save multiple objects, use the save Z function. And the Z, what the Z is referring to is the fact that it writes what's called a zip file containing multiple objects. And then there's also save Z compressed, which saves it to a zip file, but also tries to compress it after the fact. And then load to get the stuff out. And if you're loading from an object with multiple things in it, you'll get a dictionary with the keys as the names. Okay, so now we'll talk about NetCDF. So NetCDF is as I mentioned, NetCDF is a file format defined that's not Python specific, used in a lot of fields. And it basically has 3 concepts, three things you can write to the file: dimensions, variables, and attributes, with variables being the main thing you write. And you get it, there's 2 ways to get it. One through scipy, scipy.io.netcdf, and this is for NetCDF 3 files. Or the NetCDF 4 module. So what happened is basically NetCDF started out as its own file format through version, but then in version 4 decided to replace its custom format under the hood with HDF5. So from 3 to 4, there was the API, the top level API stayed the same or was similar, but the underlying file format changed dramatically. So that's why you have to, it depends what version of that CDF file you're writing, how you access it. Okay, so there's a little program called NCDump -H, which will just give you the header of the file, give you basically the metadata of the file. So right, so you see there's a dimensions block. So here I'm going to define the dimension x to be 1,000. I'm going to define a variable, an A array, a two-dimensional array with dimensions x by x. X being the dimension in the first block. And then I can attach attributes to variables. So this here means I've attached the attribute units to A equaling Kelvin. Right, so I can just say, yeah, here's an A array, it's a and it contains temperature. And I can also have global attributes that aren't attached to any variable. Okay, so and you can have multiple dimensions, multiple variables, but that's basically it. It's sort of just it's a simple format, just a flat structure. And so let's go through how to create this in Python. So okay, so we're going to create a NetCDF 3 version. So you're going to open up. So instead of using open, we use NetCDF file to open a file. I can create a global attribute by just setting an attribute on the NetCDF file object. So f.hist of this line creates a global attribute history, sets to this value. So I can create a dimension, give it the name and the size of the dimension. And then when I create a variable, give it 3 arguments: name of the variable, type of the variable, D is for double, and then a little tuple of what the dimensions of this variable are. So this is now x by x dimension, where and you have to have previously defined the x dimension. Okay, so that gives me a handle to the variable, and then I can fill it in with values here. Set an attribute on the variable, same way I did it, similar to how I did it in created a global attribute. And then close the file as usual. Okay, so pretty straightforward. And now if I want to, so that was writing the file. Now if I want to read the file in Python, similar, just NetCDF file, but in read mode. And then I can just get the global attributes by just calling, just accessing f.history. If I want to get one of the variables, I have to now look into this variable dictionary member. So f's my file handle. Look in the variables dict for variable A, and get a handle for that. And then I can access that as I would. Now this A is not a Numpy array. It's a NetCDF handle, but you can access it similar to how you would a Numpy array. And then, like global attributes, just to get a variable attribute, it's just A.units.
Is there a function for converting it to a Numpy array, or do you?
You can do this. That's what this is doing here. A colon. So if you look at the type of A, it'll be a NetCDF handle, but the type of A brackets colon will be a Numpy array. Okay. I think this is pretty straightforward. I'm not sure I'll repeat myself. Any questions on this? NetCDF for any of the file formats?
Is NetCDF also good for large text data, or is it really?
You can. I mean, you can essentially create a character array and put it in. Like what kind of data, right? I mean, it is obviously it's more for storing arrays, right? It's really geared towards because you have to set the dimensions first, right? So it's really geared for numerical arrays, but you can certainly store text data in there if you want.
Structure is more unstructured.
Yeah.
Lots of text files or that kind of stuff.
Well, if you have ragged lines,
Okay.
right? Yeah.
You could think of looking at HDF5, which is a more general format. Not everything has to be an array there, but it's a little bit more work, which now to describe structure. This assumes it's an array.
Okay. So just basically tips and summarize. Again, if your data is not text, it's better not to save it as text. It'll be faster, more efficient. And you'll want to choose a binary format for your numerical data that's portable, usually. Always good to minimize the IOPS, i.e. the number of IO operations you're performing, because there's only a limited number the system can handle. Also, every file, especially on systems like SciNet, large parallel file systems, files are actually quite heavyweight. There's a lot of metadata and a lot of bookkeeping attached to every file, and the system is designed, it's optimized for big files. So if you create millions of small files, especially millions of small files all in one directory, that really bogs things down. So for instance, you want to especially if you're on SciNet, you want to optimize for big files, and tend to keep number of files in a directory to no more than say 1,000. Now Unix lets you put any character you want in a file name, but that will usually cause problems if you then try to copy these files to other OSs. So it's best to just stick to only just letters, numbers, and underscores, just as a way of solving, saving hassle down the road. Okay, and we'll be this Thursday's topic is going to be visualization. So talking about plotting and that sort of stuff. Any questions? Yeah.
Just about the assignment quick.
Yeah.
For the version control.
Yeah.
It says use mercurial, the HT command. If we're using Git,
or Git. Yeah. You can use
fine as well.
Git's fine as well.
Okay.
Yeah. Right. Any more questions? Yeah, the homework's due Thursday by the end of class, or I guess the beginning of class.
By the end of the day, I guess.
Yeah, end of day. Okay. Okay.
Are you aware of any cases in Numpy that you have to be afraid of if you're using NetCDF? I'm just looking at a document they have describing the virtues of HDF5, and they're saying it's probably the only widely used format that can faithfully represent all of NumPy. That's from the SciPy site.
I haven't run across because NetCDF can do any attributes.
It may be some obscure corner case or something.
Yeah.
But they've got a format specification for the NPY.
Right.
NumPy save. Just curious.
Yeah, no, I'd be curious too because I haven't run across any problems.
I've started to wonder for like 20 years why my network byte order libraries are not figured out prominently.
Really?
In dealing with binary.
Well, it's
I remember a lot of the
yeah.
arguments with, well, if you take a least significant byte order float on one system, you move it to another one that's MSP or whatever you're not able to say. Okay, but every system, as soon as it has to talk on the internet, has to send stuff in,
Yeah.
right, in network byte order.
Right.
And because it's so important, they're being highly optimized functions.
Yeah.
But I don't think I found anywhere yet where anybody actually took advantage of that, because it just seemed like such an obvious thing for kind of RPC type stuff, or
Yeah.
even maybe, I don't know about scientific storage, because it would probably be optimized for dealing with integers.
Well, both basically, but yeah, for that sort of stuff, you really want to have a system. Because you typically only use it processing on that system. Not actually,
Right, well, what I'm thinking is
serving an individual.
But if you put it into HDF5 or NetCDF or something, right? If you want to go take that binary blob and put it on another system, that means internally.
Oh no,
You've either got to do it in a known byte order.
Oh no, and then
or you can have a set of rules.
No, no, and these files do.
Right.
So NetCDF and HDF5, yeah.
I don't know, it just seems like a solution that's just been skipped somehow. That was, I mean, it wouldn't offer all the other, the sort of pseudo file system kind of stuff that you get from HDF5 or something like that.
Right.
But usually when you're trying to solve a problem of this sort, you don't solve the most complicated version first, right? You stumble your way on.
Well, that's why I tend not to recommend HDF5. The number of people who actually need all those features are very few.
Yeah. Well, one of the things they were actually talking about in the document is that they were considering writing a subset library for HDF5 to sort of cover the 90% that people use.
Well, that's basically NetCDF.
Yeah, because in fact, what they were saying.
And that's what I'm kind of curious about, because really, given, I wonder about the structure, because NetCDF now these days is HDF5, right? So
right.
I mean,
yeah.
So
they eventually decided that there were that if they kept evolving NetCDF, they were going to end up with HDF5.
I think it was
an HDF5-like thing.
I think it was a combination of they didn't want to, there was probably a bit of a funding issue. Because it was, they had to pay for the development. NCAR had to pay for the development. Was paying for the development of that. And also because
format's already there rather than create another.
Right, and also because NetCDF5 had more parallel I/O work done on it. Basically using these files on, and doing clustered reads. And I think they probably felt that they couldn't, better just take the work being done there.
Right.
Than reproduce it themselves. Right. Okay, chat.
Stop the recording.
Is that what I sound like?
No, it makes you sound funny.
Yeah.
Yes, that's up to everybody.
Yeah, we got the filter on. Yeah,
it's that funny.
I should just write down this. Please tell Microsoft about this, Rob.
I just hope the recording is still somewhere. This happened the other day too. At least my son said so.
Do we have a system
that works better? Yeah.
Well, no, I mean
the little laptop works better.
Well, no, but I mean, say, given them going to Mars, are we gonna?
Oh yeah, we're gonna get. Oh yeah, this is that. That's why it's still here. Yeah. This should have been upgraded years ago.